All right, believe it or not, everything we've done so far is pretty much stuff that you did last year. Now, we're going to start talking about stuff that you couldn't have done last year. I can hear the excitement boiling in the room. What we're going to do is we're going to figure out the electric field that exists around something called a continuous point charge distribution.
It's too soon. It's just not going hard. You got nothing.
The electric field that exists around a continuous charge distribution. Now notice, this is not a point charge. It is a shape that has charge. And we're going to be figuring out the electric field that exists around it. Now, if we go back to looking at the electric field that exists around a point charge, that was kq over r squared. If we talk about as a vector, we need to add the unit vector r. So what we're going to do is we're going to take that continuous charge distribution, or that shape, and we're going to break it down to an infinite number of infinitesimally small pieces which have a charge. Who wants to guess? dq. Okay. So we are going to have an infinitely large number of infinitesimally small charges dq. In other words, dE is equal to k times dq over r squared times unit vector r. Right? So what we're doing is we're saying each one of the little charges dq has an electric field which is defined by a point charge, and that is, in this particular case, dE. If we take the integral of both sides, we get the integral of dE is equal to the integral of k dq over r squared unit vector r. You can see that k is a constant, so we can bring that out from the integral. And the integral of dE is just the electric field. So the electric field equals k times the integral of dq over r squared times unit vector r. This is how you figure out the electric field that exists around a continuous charge distribution match.
Why is the unit vector like under the integral?
Why is the unit vector under the integral? Because the unit vector, I don't know, because the unit vector usually goes at the end.
Okay. Is it like part of the integral or no?
Kind of depends. Go through.
Well, like if it's just direction though, like how can it be part of the?
We'll give it time.
Okay.
I can't like, tell you everything all at once. Okay, so please notice this is not on the equation sheet. But this one is. Right? So, I mean, they really just follow. It's just one is for a point charge, one is for a continuous charge distribution.
So can you memorize it, or do we have to derive it?
No, that's just one. I mean, it's just follows directly from there, so that's fine. You can just use that. Thanks. Good question. All right. So now we have the same issue we had with moment of inertia and center of mass. We have the integral with respect to q, and we have r. Right? Before we had the integral with respect to mass, and we had r. So it's the same type of issue. So I introduce three new types of density. First one is called volumetric charge density, the symbol for which is a lowercase rho. It's equal to q divided by v for volume. This is volumetric charge density. Hi. There's a lot of hubbub today. If you'd like to help, that's fine. Go ahead, Michael. Symbol? Actually, lambda is, sure, linear charge density we need to do on the middle, but that's fine. Go ahead. Is equal to?
Over air, or no. What? L.
Q over L. We have surface charge density. What is the symbol for surface charge density, Zach? Lowercase sigma. So this is surface charge density. Linear charge density. And the dimensions are coulombs per meter cubed, coulombs per meter squared, and coulombs per meter for our various types of densities. And hopefully, this looks familiar.